So good morning everyone. I'm Arnav Arora, BTech Engineering Physics, and this is a presentation on diamond sensors, which is part of the course PHN 310 Applied Instrumentation. So diamond NV centers are nothing but a substitutional defect in diamonds, which happens very commonly and can also be done artificially. Basically, a carbon is replaced by a nitrogen in diamond lattice, and another adjacent carbon, which is just to the side of it, is kicked out of the lattice, which creates a vacancy here. This is what you call an NV center, but for all our purposes, we dope this NV center with an extra electron to make it have exotic properties that can be exploited. So in total, there are 6 electrons associated with the NV center, one coming from each carbon, so that's 3, 2 of them coming from a nitrogen, that's 5, and one extra electron that we've doped in the vacancy. So this means it's a 6 electron 6. MS equals plus minus 1 state belonged to the microwave regime. So if you keep on shining a microwave radiation and keep on changing its frequency, let's see how we can use this asymmetry for some different stuff we can do with NV centers. So the first is optical spin polarization. Now, optical spin polarization is used for state preparation of an NV center. So if you have a system that you want to use as a sensor or any other thing, you should have the ability to create it into any state that you want to. And in this state, we have the ability to create it into the MS equals 0 state. So what you do is that you keep on shining light on an NV center, and all the states would finally reach MS equals 0. Let's see why this happens. So let's say that you had 100 NV centers with you, and the worst thing that would happen is that 50 of those NV centers are in MS equals 0 state, and 50 of them are in the MS equals plus minus 1 state. Now you keep on shining a light on it. So when you shine a light on it, which corresponds to, let's say, red or greater wavelength, then it would excite electrons from the ground to the excited state. So all of these 50 electrons would move up and reach the excited state. Now from here they would start to decay back again, and there are the two pathways that they can take. They can do a radiative decay back to the ground triplet state, or they can go to the singlet state. So now, because there is a disproportion in the decay, out of the 50 MS equals plus minus 1 states, 40 of them come to the singlet state, but out of the MS equals 0 state, only 30 of them come to the single state, which gives you a total of 70 here, right? This is because there is an asymmetry in these transitions, and the rest of them, they go to the ground state over here. So because 40 of the MS equals plus minus 1 states came to the singlet one, only 10 of them would come to the ground triplet state, and 20 of them would come to the ground triplet state of MS equals 0. Now these 70 would move back to the ground state again through non-radiative pathways, but now you see in total you have 45 electrons in the MS equals plus minus 1 state and 55 electrons in the MS equals 0 states. So you were able to create this disproportion over here, and if you keep on shining light, this would keep on happening again and again, and finally you would have all the electrons in the MS equals 0 state and the nothing in MS equals plus minus 1 state. So this allows you or gives you an ability to initialize these NV centers. So next, let's see about spin polarized fluorescence. So simply because there are more transitions that would happen from the MS equals plus minus 1 state to the singlet state than the MS equals 0 state to the singlet state. This means that there would be more transitions that would happen. The radiative transitions of MS equals 0 state would be more than the MS equals plus minus 1 state, right? So if you have 50 electrons, you pump them all up with a green light. So green light has a greater energy than red light, so you would pump them up even above the energy difference. They would relax down to the energy levels and then come back down with red light. but you would see that only 10 of them would come over here, but 20 of them would come here. This is because of the asymmetry again. So this means that you can always read out which state you are in. If you shine green light, you would get back red light, and the intensity or the difference in intensity relative to some value can tell you whether you are in the ms equals plus minus 1 state or you are in the ms equals 0 state. See, let us say you start with a very low frequency. This frequency does not correspond to the microwave radiation, so you get some fluorescence, and you keep on increasing this frequency until you hit a point where you have reached the microwave frequency, which corresponds to the energy difference between ms equals 0 and ms equals plus minus 1 state. At this point, you would start exciting electrons from ms equals 0 to ms equals plus minus 1 state, and the ms equals plus minus 1 state would start to get populated. And as we learned in the previous slide, that the intensity of light that comes out of ms equals plus minus 1 state is lower than the ms equals 0 state. You would see a sharp dip in this intensity over this frequency. When you increase this frequency further, you would detune out of the ms equals 0 and ms equals plus minus 1 transition, and again you would see an increase in the frequency, which corresponds to the fact that it is in ms equals 0 state. So yeah, this is the microwave spectroscopy of NV centers, and with this you can get to know what is the difference between the microwave regime difference between the ms equals 0 and ms equals plus minus 1 state. So now we have all the ingredients to do magnetic field sensing. So in the presence of a magnetic field, the ms equals plus minus 1 state, which were originally degenerate, they also split. So this is due to an effect called the Zeeman effect, which is I hope very common and everyone knows about it. So depending on the direction of the magnetic field, one of the levels would go to a higher energy and the other would go to a lower energy. And the degeneracy of this ms equals plus minus 1 state is lifted. So what are the consequences of that? So because the degeneracy is lifted, there are now two microwave transitions that can happen. Earlier there was only one, so we saw only one dip in the microwave spectroscopy, but now there are two transitions that can happen. So you start shining microwave radiation as well as green light, and you get back red light, and you keep on noting its intensity. Let us say that the magnetic field points in the z direction, then the minus 1 state would be at a lower energy and the plus 1 state would be at a higher energy. So you reach a frequency which corresponds to the transition between the ms equals 0 and the ms equals minus 1 state, and at that point you see a dip in transition. This is because the minus 1 state is being populated, and we know that the intensity of minus 1 state is lower than the ms equals 0 state. So you would see a first dip, but then you would see that it rises again because you're detuning out of the this transition frequency. Then you would see another dip in your curve. This corresponds to the transition between ms equals 0 and the ms equals plus 1 state, which is higher than the minus 1 state. So you would see another dip in your transition, again due to the fact that its intensity is lower than the ms equals 0 state. And then when you started increasing, you detune out of all possible microwave transitions, and you would again have a higher frequency over here. So the difference between these microwave frequency directly corresponds to the energy splitting of the ms equals plus 1 and the ms equals minus 1 state, which is linearly proportional to the magnetic field. This comes from the Zeeman splitting of the magnetic field. So you have a system where you can just shine microwave radiation and green light, note the intensities, calculate the difference in the peaks, and that is linearly proportional, which is very good in instrumentation to the magnetic field itself, and it can be used for very precise magnetic field sensing. So this is all okay that you can measure magnetic field in one direction, but how do you measure magnetic field in 3 dimensions? You can do that also. So the vacancy, the NV center that is created in an carbon atom or in a diamond is different, can be done in different orientations, right? So there are 4 orientations that are possible, which corresponds to 4 different chiralities. And so let us say that you have an ensemble of NV centers. You have many NV centers, and because they have been created by some chemical process, you cannot control which direction the NV center would have. That means you have a random ensemble of different NV centers with different directionalities. If you apply magnetic field to this, and then you do microwave spectroscopy on this, depending on the three components of the magnetic field, whichever aligns with whichever NV center, you would have different magnitudes, because you would take different projections of the magnetic field which are along the direction of the NV centers. This means you would have 4 different transitions in your system corresponding to the 4 directions, and using these 4 different transitions and differences between them, you can calculate the full 3-dimensional magnetic field present in the system. So why are we talking about NV centers, and why are we excited about them? So the thing is that the NV centers are highly sensitive to magnetic field. This is because this is happening at the most fundamental scale, that is the electronic spin. They can measure changes in magnetic fields up to few nanoteslas, which is not possible with current technologies. Nanotesla is a very, very small quantity. And because it has the sensitivity of nanoteslas, you can create a sub-micron level 3-dimensional map of a magnetic field. So think about creating maps of magnetic field, full 3-dimensional fields of like a piece of tissue or a very small part of the brain. That cannot be done with even today's MRI machines, but can be done with NV centers. And the reason why an NV center basically works is the fact that it is like an isolated atom, right? This Zeeman splitting exists since more than 100 years, and people have known about it, but they haven't been able to use it, because if you have a real atom or an atomic system, then there is broadening in the system. Atoms are interacting with other atoms around it, and so because of these interactions, the transitions would get broadened. But over here, the fluorescence peaks and the transitions, they do not get broadened at all, and they give you very precise values with existing technology, and that is why the NV centers are so sensitive to magnetic fields. And with NV centers, it is possible to create nanoscale MRIs, which can detect magnetic fields at a molecular level. So if you have even a single piece of tissue, you can create the 3-dimensional map of magnetic field that is inside of that tissue. You can also create a GPS system that does not require satellites. So the way this is done is that you create a map of magnetic fields all around the Earth, and then you can compare the magnetic field at your location to this nanoscale magnetic field map of the Earth and know where you are. This does not require any satellite communication. There are also many other things that you can measure using an NV center. So just like magnetic field, electric field also couples to the NV center through what we call the Stark effect. This means you can measure 3-dimensional electric fields in your system, and this can be easily integrated into existing CMOS technology, because NV centers are carbon, which are very well compatible with silicon, and you can use it for nanoscale electric field measurements in your nanoscale devices. NV centers also coupled to strain applied to them, and this can be used for 3-dimensional strain measuring. You can measure the full 3-dimensional strain tensor with this. You can also do like spatial mapping of temperature, so creating like a scalar field map of temperature, because even thermal coupling to NV centers is possible with very high sensitivity. So basically, it's an integrated platform which can measure all fundamental electrodynamic, mechanical, and thermal quantities. You have one system and one technique which can measure so much. Yeah, thank you.